Hi everyone, welcome once more to this YouTube channel, Best Science Brain YouTube channel. Today we are going further to look at chemical kinetics, an aspect of physical chemistry. In today's lecture, we're going to learn how to obtain the integrated form of first order reaction. The integrated form of first order reaction. So this lecture is meant for those in second year in high institution offering science or chemistry or related courses, biochemistry, microbiology, and also it also meant for those who are offering their postgraduate studies or the MSc courses in chemistry or biochemistry. Then the integrated form, that the derivation of integrated form is meant for these people I just mentioned, while the calculation aspect of it is meant for all science students in tertiary institution, both those in first year, second year, and also in postgraduate or PG programs. So we'll go where we'll start. A first order reaction is a reaction in which the concentration term in the given rate equation is raised power 1. So as we explained in the first video on chemical kinetics, a reaction is first order when the concentration term in the rate equation raised power 1. So we say let us consider the hypothetical unimolecular reaction given below. So as we said, a reaction is unimolecular when it involves one reactant particle. For instance, you see A, one particle of A going to produce. So since one particle of A or one atom of A is involved, that example represents a unimolecular reaction. So from this reaction, we're going to first of all obtain the rate equation, the differential rate equation. We know in chemistry that the rate of reaction is nothing but the change in concentration per unit time. So the differential rate equation of this reaction is going to be dA, that D means that the change in concentration of A over change in time, as we can go to see. So the rate equation again as R being the rate of reaction equal to dA, meaning change in concentration of A. In chemistry, the bracket sign there, that square bracket where A is placed, that square bracket represents its pronounced concentration, while the substance A is the reactant in the equation. So square bracket A is pronounced or interpreted as concentration of A, and that D in front means change, delta signifying change in concentration of A, final concentration of A minus initial concentration of A, that means not change, over change in time. So rate is the change in concentration of a substance over change in time. So equal to, I will know that the rate of reaction is proportional to the concentration of the substance. So rate dA over dt equal to K, then A in bracket. So that A in bracket A means concentration of A, while the K there is called the rate constant. So you see that expression. That expression represents the rate equation or the rate law for the hypothetical example we have above, A giving us product. So we'll come back to the other equation 1. Then we'll know why we have a minus sign. From our first video, we say that when we write the rate equation with respect to the reactant, A is the reactant, we put minus sign. That minus in front of the A represents or shows that the concentration of A or the amount of A being used depletes with time. As reaction progresses, the reactants are consumed. The concentration of the reactant continues to decrease as the reaction progresses. So when you write a rate expression with respect to the reactant, you must have a minus sign. So since A is used being a reactant, that minus sign shows that the concentration of A is decreased with time. So we have minus dA over dt. Negative sign shows that the concentration of A is decreasing with time, equal to Ka. Now, we now say let the initial concentration of the reactant A at time 0. Initial concentration means the concentration of A before the reaction started. So initial concentration of A at time 0 be equal to small a in square bracket. So that square bracket A means concentration of the substance A before the reaction started at time 0. So becomes A, small a in square bracket, mole per dn³. Now we say let the concentration of the reactant A that has decomposed into product at time T equal to S mole per dn³. What does it mean? As the reaction progresses, the amount of the reactant will continue to decrease because the reactants are being converted to product. Let's say after some time, T being equal to T, that time could be 5 seconds, 5 minutes, 10 minutes, and then let's assume that after some time, when the reaction has commenced for some time or has continued for some time, S moles of A have been changed to product. So that S mole per dn³ there represents the concentration of A that has changed to product after some time of reaction. Then we say therefore the concentration of A remaining at time T. So if S mole had decomposed to product, and we started with A, small a mole, that is that you see it there. So we started with A moles of A, and after some time, S moles of A had changed the product. Then what amount of A will remain? Therefore, the concentration of A remaining after that time T will now become A minus S. Why is it A minus S? Because we started with, initially, before the reaction started, we have A moles of A present. After some time, S moles of A have decomposed the product. So the remaining amount in the reactant A becomes A minus S. That is small letter A minus S. That becomes the remaining concentration of A after some time. We'll go through it again. We said, let the initial concentration of the reactant at time 0, that is, before the reaction started, we'll have A moles of A. A means, this A we're talking about is the small letter A in bracket. A moles of the reactant A present. Then, when the reaction has commenced for some time, let's say the time is T, could be any time interval. Then let's assume that S moles of the reactant A has decomposed. So we'll say, let the concentration of the reactant A that has decomposed into the product at time T be equal to S mole per dn³. Therefore, the concentration of reactant A remaining at time T will now become small a, which is the original concentration, minus S, which is the concentration of A that has decomposed. Concentration of the reactant, that is reactant A that has decomposed. So we'll now have that. So having done that, from equation 1 is the equation we had before. For equation 1, substitute the concentration of A, big A, in bracket with A minus S, small a minus S. So we now have equation 2. So we have equation 2. What do we do to, how do we get equation 2? We went to equation 1, dA, where we have capital A. Replace capital A with A minus S. That A minus S represents the concentration that is present at time T. So we'll come back. We now have this, that is substitution, replacing big A with A minus S on both sides. We now have A minus S here and also A minus S on the other side. So that is it. So having obtained that, that is equation 2. We expand the expression. We expand the equation 2. We expand the left hand side, that is D bracket A minus S all over dt. We open the bracket. So we say expand the expression D A minus S in the above equation 2 and separate variables to obtain equation 3. So let's see how the expansion was done. To expand it, we multiply D after the bracket by A. So D times A gives us dA. So we'll have go down. We now have dA over dt. We separate the dt. So we'll go again and say minus, that is here, okay, D times minus minus S give you plus S. We go back again, we now have plus ds over dt. So that dt being the denominator there is given to both dA and dA, that is separating the variables. We now have dA over dt plus ds over dt equal to the right hand side, which is k into small a minus s. We now obtain our equation 3. So having obtained equation 3, what do? We now take the construct of small a, that is square bracket a, small a, as a constant. So we want to differentiate dA over dt. D bracket small a over dt. We differentiate it, but since we are taking that initial concentration small a as a constant, and in mathematics the derivative of a constant is 0. So we say the derivative of a constant is 0. That means the a over dt, if you differentiate it, since a is a constant, we get 0. So we now have that expression dA over dt 0. So if the a over dt becomes 0, that means the a over dt in equation 3 will vanish. And what remains is now ds over dt equal to k a minus s. So equation 3 now turns to ds over dt equal to k bracket a minus s. Since the a over dt is taken as a 0, since a is a constant, we now obtain equation 4. Then having obtained equation 4, what do? We'll cross multiply. Cross multiplication of equation 4 gives equation 5. Look at equation 4, then come down and see where the multiplication was done. We have the s over dt on the left hand side, k bracket open small a minus s on the right hand side, and then of course the denominator of k a minus s must be 1. We place 1 under it and then do our cross multiplication. So the s times 1 will give us the same ds, which you see on equation 5. Y dt multiplied by k into a minus s give us k a minus s times dt. So having obtained that, we now divide both. This is equation 5 now we have obtained. So having obtained equation 5, we divide both sides of equation 5 with a minus s to get equation 6. So look at equation 5, divide both sides of equation 5 by bracket open, the square bracket opens a minus s, divide both sides by a minus s. So when we do that, we now have ds all over a minus s inside square bracket, k multiplied by a minus s multiplied by dt all over also the same a minus s under dividing both sides by a minus s. So look at the left hand side of that expression. A minus s in bracket cancels a minus s. So the right hand side, please, a minus s cancels a minus s because they are equal. We are now left with k dt on equation 6. I will bring down the left hand side as ds all over a minus s on equation. That is equation 6 given to us there. So having done that, we now proceed to integrate. We now integrate. We integrate equation 6. That equation 6. So we can have this, look at it, erase. Then integrate equation 6 above with the limits s equal to s and s equal to 0 for the left hand side, and limits t equal to t and t equal to 0 for the right hand side of the equation. So you can see the integration sign. This equation 6 are turned to equation 7. The integration sign, we integrate with limits s equal to s and also s equal to 0. We also integrate the other side. We bring k out of the integration sign symbol. K is off on the right hand side because k is a constant. So we now have t equal to t and t equal to 0. We now integrate dt. So having done that, in order to understand, so this topic has to do with calculus of mathematics. So in order to understand how to integrate this expression, we need to go back to our calculus or integration aspect of calculus. So it reads, in order to understand how to integrate the above equation 7, we have to revise our calculus in mathematics. So we're going to look at a brief revision on calculus. So in calculus, if you integrate a differential If you integrate the s, you get s. If you integrate the a, you get a. If you integrate the t, you get t. So look at the example there. Integrate the s, you're going to get s. Then plus c, that is called the constant of integration. So in the above example, looking at the right hand side, if I should integrate the t, I will get t. So if you integrate the differential, you get the value on that differential. If you integrate the t, you get the t. Just like the instruction we gave, if you integrate the s, you get s. Then we'll now look at other example. Now this takes care of the right hand side of the equation 7. Now let's look at the left hand side of the equation. Left hand side. For us to understand the left hand side, we have to look at the standard integral. If you have this example, integrate the s over s. The same thing as saying integral of 1 over s ds. That is separate, push the ds. The quotient of ds is 1, so 1 over s ds. The ds over s, same thing as saying 1 over s ds. If you integrate 1 over s, is the standard integral, a non-integral, you get natural log s. I'll pronounce that ln, natural log. I'll call it ln. I'll call it ln s. If you integrate 1 over s, you get ln s plus c, where c the constant of integration. Now, having known the standard, then if we integrating having known the standard, if you are now integrating this one, the s all over 1 minus ks. You see that this one is somehow different from the one we did above, the standard, which is the s over s. But it's just a little bit modification. The s all over 1 minus ks is equal to, push the ds aside. The quotient of the s is 1. It now becomes 1 over all over 1 minus k. The same principle applied above. Then you're now integrating 1 over 1 minus ks. You now have ln natural log of 1 minus ks, similar to 1 over s, giving us ln s plus c. We'll come down, we now have ln 1 minus ks plus c. But look at the value got after the integration. There is minus k in front. How did I get the minus k? Look at what you're integrating, the denominator, 1 minus ks. The quotient of the s under is minus k. So you multiply the answer you got, the ln 1 minus k by the coefficient of s under, and that will give you minus k into ln 1 minus ks. So when you have this sum, the same ln of the integral give you ln of what you are integrating, what you have on the denominator, ln of it. Then you have to multiply the answer by the coefficient of s. So minus k, where that k should be a whole number or an integer. So if the minus k is 2, I will have minus 2 ln 1 minus 2s. If the k is 3, I will have minus 3 ln 1 minus 3s, then plus the constant of integration. So where I said k is an integer or constant, and c above is the integration constant. So let's look at this illustration, an example. We have integrate the s all over 1 minus 2s. Integrate the s with respect to s anyway. 1 minus 2s under. So we have it, we'll separate, put the ds aside, and then the quotient of the s is 1. The 1 will now be on top as the numerator. Then following the process I described, it's going to give us ln or natural log of 1 minus 2s in bracket plus c. Yes, but if you look at the denominator there, the coefficient of s is minus 2. So we multiply by the coefficient, now have minus 2 ln 1 minus 2s plus c. So having understood that, we can now go to our above to our integration and what we've been doing. So we're applying the above integration law to the left hand side of equation. equation 7, we then have, so the equation 7, let's go back to equation 7, which is the one we left. Okay, look at it. The left hand side, you can see, if you integrate it now, you see that it's more like the one I just given you. The left hand side, which is ds all over a minus s. If you integrate it, you're going to have ln a minus s. Yes, because of the form where I created. But if you look at s here, the equation of s, in that place I click now, of s, in front of s is minus 1. So if you integrate this expression, the s over 1 minus s is going to give us minus 1 multiplied by ln a minus s. If I integrate this one, the right hand side, if you integrate dt, as I told you, if you integrate a differential, you get the value of that differential. So if you integrate dt, you get t. So let's go back to where we are supposed to be. So that is it. That is that. So if you integrate that, you have ln a minus s. What you integrate was 1 over a minus s. We have ln a minus s. And since the coefficient of s is minus 1 in that expression a minus s, so the number in front of s is minus 1. You multiply it by minus 1. That's why you have the minus outside. Then the boundaries or the limit you are integrating, remember from initial, s is equal to s and s is equal to 0. Then the right side, what do we integrate? Integrate dt, you get t. And then k is outside the integration sign. You now have k multiplied by t, taking t, the boundaries or limits, t to be equal to t and t to be equal to 0. We now substitute the limits into equation 8. The limits, that means for the equation, let's concentrate on the left hand side first. On the left hand side, I'll replace s with s and also replace s with 0. So you can see the working there. Under, you have minus ln a minus s. So if s is equal to s, replace s with s, you see how the same thing. Then minus ln a, replace s now with 0. So a minus 0. So replace the value of s with s and also the value of s with 0 and subtract the 2. That's what I did here. So ln a minus s, replacing s with s, we still give the same s. And replacing s with 0, we have a minus 0, subtract the 2. And remember there's a minus sign already outside the bracket for my integration. The minus sign is still there. Then going to the other side, the right hand side of the equation, replace t with t and also replace t with 0. That k covers all. When I have k equal to t, if you replace t with t, you still get t minus, then 0, replace t with 0, and I have 0. So solving out this, and I have minus, open the bracket. So the first term there on the left hand side becomes minus ln a minus s. Then the middle term has a minus sign, but there's a minus in front covering the whole bracket. So minus up, go up. The minus in front, multiply with the minus at the middle gives you plus. You come down and see plus. So that's why the middle minus change to plus. Then ln a minus 0 gives you a equal to kt, because t minus 0 gives us the same t. We are obtaining equation 9. Now we rearrange equation 9. How do I arrange equation 9 to get equation 10? I place the a in front. Look at it. Ln a was placed in front, and then minus ln a minus s was pushed behind ln a, equal to kt. Then applying the law of logarithm, we want to bring two log of the same base together. When you have minus sign, you change it to division sign. So taking only one ln, when I have ln a all over, that minus makes it become division all over a minus s, and the two of them are now inside one log, equal to kt. That gives us equation 11. Then, having done that, from mathematics, the relationship between natural log, that is our ln, natural log, which we call ln now, of a number, ln s, and the logarithm of a number to base 10, that log s. The two of them are not the same, but they are related. So we can convert this ln on equation 11 to natural log, to log of base 10. This is natural log to log of base 10. But how are they related? The relationship given to you in the next slide. Ln of a number is equal to 2.30 log of a number. So ln s is written as 2.30 log s. So look at equation 11, the one we derive above. It's also written for you again. Ln a all over a minus s equal to kt. We are going to change that ln to log. What do? Wherever we see ln, we replace it with 2.03 log s, or log of the number. So that ln is changed to 2.30 log. Look at the connection between equation 11 and equation 12. So ln was replaced with 2.30 log. So that is it. Equation 11 and equation 12 are the integrated form of first order kinetics. So as you have it read down there, say either equation 11 or 12 represents the integrated form of first order kinetics. You can see that. Or first order reaction or kinetics. So any of them, it can be expressed in terms of natural log or ln as equation 11, then in terms of log to base 10 as equation 12. So both of them are the integrated form. Any of them represent the integrated form of first order kinetics. So now we're going to look at mathematical problems on first order kinetics. Having derived the rate equation or the integrated form of the rate equation, we're going to look at how to apply those equations 11 and 12 we derived before, how to apply it to solve mathematical problems on first order kinetics. So it reads, having derived the integrated form of first order kinetics, we can proceed to solve mathematical problems with the integrated forms given by equation 11 or 12. However, we need to first simplify the above equations. So before we start applying equation 11 and 12 to solve problems or mathematical problems on first order kinetics, we have to make these equations simplified. So we said the concentration of the substances at time 0 taken as initial concentration represented by in equation 11 and 12 as A, that is a square bracket small a. As we said initially, that square bracket small a represents the initial concentration before the reaction began, or that time 0. Then we can now say let that A, that initial concentration of the substance, let it be equal to AI. So that small bracket I is now written as, or is now modified as A square bracket small ai, where that small I means initial. So if I should pronounce it, it just means initial concentration. Just a little change. Then the concentration of the substance at time t equal to t, represented in equation 11 and 12 as A minus S. Then in our modified equation now say let A minus S be equal to small a in bracket t subscript t, where A square bracket small a subscript t represents concentration of the substance at any given time. So we're going to now change equation 11 and 12 to a different form. Equation 11 and 12 are all modified as follows. So equation 11 that says ln A small a in bracket, that is concentration of A, initial concentration of A, all over A minus S equal to kt, that equation 11 now becomes ln square bracket A, then subscript I, meaning initial concentration, replacing the small a up with A, then with subscript I, and then replace A minus S under as square bracket AT. That's the only difference we are making here, equal to kt. That gives us equation 13. Then equation 12 we derived before that says that is when you convert the ln to log, 2.303 log square bracket small a, that initial concentration, all over square bracket small a minus s equal to kt becomes 2.30 log. They replace the small a on top to be ai, meaning initial concentration, and replace a minus s to be equal to at equal to now kt, giving us equation 14. So you see that equation 13 and equation 14 are modified forms of equation 11 and 12. So in calculations, we prefer to use something that's simplified. So that will modify equation 11 and 12 to equation 13 and 14. Equation 11 modified to equation 13 and equation 12 modified to equation 14. Simply by changing the a in this equation to be ai, which means same thing, and also a minus s to be equal to at, which means concentration resultant at time t. To say for convenience, equation 13 and 14 can be applied in solving mathematical problems on first order kinetics, as I said. However, we shall be applying equation 14 in this tutorial. So we shall be making use of equation 14, the one that has log to base 10 in this tutorial is this one here. We prefer to use equation 14 here instead of equation 13. So they use one of the equations. 13 and 14 can be used, but they use 14 to avoid creating complications or confusion in understanding. Exercise 1 says the conversion of cyclopropane C3H6 to propene has been studied to follow a first order kinetics with experimental rate law R equal to K C3H6. You look at that rate law before you even continue the equation. That rate law shows that the reaction is first order reaction. How do you know that it's first order reaction? You look at that CH3 where my cursor is now. The power to which the cyclopropane C3H3 is raised to is 1. So there's nothing on it. That means the power on it is 1. And for first order reaction, the concentration term must be raised power 1 in the rate equation. That shows that this is first order reaction. So let's continue. If the initial concentration of cyclopropane is 0.05 molar or mole per dm cube, how many hours must elapse for the concentration of the compound to drop to 0.01 mole per dm cube? The rate constant K is 5.4 times power minus 2 per hour. So what are we looking for in this question? We're looking for time. How many hours we take the concentration to drop from 0.05 to 0.01 molar solution or mole per dm cube. So let's look at the solution. The rate law of the reaction given as R equal to K C3H6 in square bracket given to us. And if you look at this rate law, as I explained before, is a first order kinetic because the concentration C3H6 is raised to power 1. Okay. Shows that the reaction is a first order kinetics. Okay. Now for my problem, the initial concentration of cyclopropane, which in the rate equation, which is written as square bracket small a and I at the meaning initial concentration, then we can rewrite it as replace the a in the square bracket small a with C3H6 and then you have I. So replacing it, modifying that expression square bracket a. Since the substance we're dealing with cyclopropane, so replace the a with C3H6, then the initial concentration is given to us as 0.05 mole per dm. This is given to us in the equation. Then concentration of cyclopropane at time t. The time t is the time we're looking for, which should be given as in the rate equation as square bracket small a and then t outside. It can be written as square bracket C3H6 then square bracket t. It given to us in the equation as 0.01 molar solution. All these are given to you in the equation. You can see cyclopropane is if the initial concentration is 0.05 molar, how many hours must elapse for the concentration to drop to 0.01? So you see the initial concentration is 0.05, the concentration at the time 0, and then the concentration after some time is 0.01. So that's why you have this. So having done that, we are looking for time. That's why question mark is on time. And then the rate constant given to you in bracket. The rate constant is 5.4 times power minus 2 per hour. So modify equation 14 with the substance cyclopropane. So look at equation 14. It was brought down for you again. The equation 14, which is the derived integrated rate form of first order reaction, 2.303 log A I, that is initial concentration, all over A T. Consider time T equal to KT. We're going to modify it. How to modify it? We're going to replace A in it with C3H6. Look at the numerator on equation 14. That A, and then look down, replace with C3H6, initial concentration of cyclopropane, and then the A under AT also have C3H6T. That's the concentration of time T equal to KT. So equation 14 will modify to get the equation under it. Then we now have substituting the given values into the modified equation. We have the values we listed. We substitute 2.303 log the initial concentration of cyclopropane C3H6 is given to us as 0.05. Replace with 0.05, and the concentration of the substance at time T is 0.01 given to us. Replace concentration of cyclopropane C3H6 with 0.01. Look at the equation we are looking at now, equal to the rate constant K is given to us in the question as 5.4 times 10 to the power minus 2, and then T multiplied by T. Since we're looking for T, we go ahead. 2.303 equal to log 5. How do we get log 5? Above 0.05 divided by 0.01 give you 5, equal to the right hand side 5.4 to the power minus 2T. Then log 5 from 4 figure table or from your calculator. Log 5 is 0.6990. So we now have 2.303 multiplied by 0.6990 equal to the right hand side 5.4 to the power minus 2T. Then 2.303 multiplied by 0.6990 give us 1.6098 equal to 5.4 to the power minus 2T. We now make T the subject. How do we make T the subject? Divide both sides with 5.4 power minus 2 to make T the subject of the formula. So we divide both sides by 5.4 to the power minus 2. So we now have 1.6098 all over 5.4 to the power minus 2 on the left hand side. Also 5.4 to the power minus 2 divided by the itself, 5.4 to the power minus 2. You see that on the right hand side, 5.4 to the power minus 2 cancels out 5.4 to the power minus 2, remaining T. So T now becomes, you divide the left hand side, 1.6098 by 5.4 to the power minus 2, you get 29.8 hours. So time is 29.8 hours, approximately 30 hours. So it's going to take 30 hours for the concentration of 0.05 molar of cyclopropane to reduce to 0.01 as asked in the question. We have another example to look at now. Exercise 2 says the decomposition of compound SO2 CL2 is the first order reaction. Look at the equation showing its proposition. SO2Cl composes into sulfur dioxide, SO2 and chlorine. So it has a rate constant of 0.17 per hour. The initial concentration of SO2Cl2 is 1.25 times per minus 3 mol per kg. How long will it take the concentration to drop to 0.31 times per minus 3 mol per dn cube? So look at the question very well. So having done that, we go to the solution. It says, since the reaction is first order, the initial rate law of the reaction should be of the form R K SO2Cl2. So they did not give out the rate law, but how to write the rate law. Since the first order, and in rate law, we connect the rate of reaction to the concentration of the reactant. The reactant is SO2Cl2. So since it's first order, the concentration of SO2Cl2 will raise power 1. So it's a first order kinetic. So initial concentration of SO2Cl2, which of course the symbol A subscript I stands for initial concentration. We replace A with SO2Cl2, then subscript I, and that will give us the initial concentration given to us in the equation as 1.25 power minus 3 mole per dnq. Then the concentration of the same compound SO2Cl2 at time t, which you can write as AT in the formula. The equation at time t, replace the A with SO2Cl2, then T subscript. That means concentration of the compound at time t given to you in the equation as 0.31 to the power minus 3 mole per dnq. Then we're looking for time. So this question is more like the first one we solved. Looking for time, how long it take the concentration to drop from 1.25 to the power minus 3 to 0.31 times the power minus 3. We're looking for time. And the rate constant given to us as 0.17 per hour. So all these values are given in the equation. You look at the equation again. Look at this. After the equation, you see it has a rate constant of 0.17 per hour. That is our K. If the initial concentration of SO2Cl2 is 1.25 power minus 3 mole per dn cube, how long, that is time, will it take the concentration to drop to 0.31 times power minus 3 molar solution? So having done that, we now have the equation 14, that the integrated equation, rate equation for first order, which says 2.303 log A initial concentration AI all over AT, concentration at time t equal to KT. So that equation for T will bring it down again. Then replace A in that expression on the left hand side, replace the values of A with the compound SO2Cl2. So we now have 2.303 log SO2Cl2, then subscript I, meaning initial concentration, under it SO2Cl2, then subscript T, meaning the concentration at time T equal to KT. We now make our substitution from what the values provided in the equation. We have 2.303 log 1.25 to the power minus 3, which is the initial concentration, all over 0.31 to the power minus 3, which is the concentration at time T, equal to 0.17, which is the rate constant per hour times T. So we'll simplify further. So we now have 2.303 log, you divide 1.25 by 10 to the power minus 3 by 0.31 to the power minus 3 divided 2, you're going to have 4.032 equal to the right hand side 0.17 T. We now find log 4.032, and that will give us under as 0.6055 multiplied by 2.303 equal to the right hand side 0.17 T. Then we apply 2.303 by the log of that value 0.6055, going to have 1.394 equal to 0.17 T. We make T the subject, divide both sides by 0.17 to make T the subject of the formula. We now have 1.394 over 0.17 and then 0.7 over 0.7, 0.17 over 0.17. So 0.17 cancels out, then T becomes equal to 8.2 hours. That is it. We'll now go to the next exercise 3. So as the video is going on, if you're not subscribed to the channel, look up to the channel name, Best Science Brain. Under it, you see a subscription button or bell. Tap on it once and get subscribed for more video notifications. Okay, we'll go to the next exercise that says the sugar sucrose decomposes in acid solution to simple sugars, glucose and fructose. You can see the equation C12H22O11 plus water. C12H22O11 oxygen oil is the formula for sucrose. So it's hydrolyzed or decomposes to give you the isomeric monomers or units, glucose and fructose. So they are hexoses, they have the same formula. C6H12O6, C6H12OC. The same formula, they only define their structures, they are similar to each other. So The hydrogen ion on top of the arrow indicates the presence of acid. So that is the reaction. So they say the rate equation will go down. The rate equation is giving us initial rate R equal to K, bracket opens, formula of sucrose, C12H2O11, bracket closes. From this rate equation, we see that this reaction is first order because the rate of reaction, the concentration in the rate equation is the sucrose in the square bracket, C12H2O11, raised power 1. So it's a first order kinetics. And we see that the reaction does not even depend on the concentration of water or acid. So that means the power to which the concentration is raised in the rate equation determines the order. So it's a first order kinetics. So we now say where the rate constant is 0.21 hours. So our K is 0.21 hours. 21 per hour. That should be per hour, not hours. So we can make the correction per hour. So 0.21 per hour. Okay. We are now asked if the initial concentration of sucrose, that is 0.01 mole per dn cube. That means the concentration of sucrose at time 0 before the reaction commenced is 0.01 mole per dn cube. They ask what the concentration of sucrose after 5 minutes. So in this question, we are not looking for time as in the first two examples. We are now looking for the concentration of the substance sucrose after some time, after 5 minutes. So we'll go to the solution. We say the reaction is first order because the initial rate of reaction is giving us R equal to K C12H2O11 in square bracket. It's first order because that sucrose in square bracket raised power 1, making it first order kinetic. Now, initial concentration of sucrose C12H2O11, which can be written as AI, where in this time around A is your sucrose, C12H2O11, then I means initial, is given to you in the equation as 0.010 mole per dn cube. That is it. Then the concentration of sucrose after 5 minutes. 5 minutes is the time given to us in the equation. AT. Replace the same A with the same sucrose, C12H2O11. T is unknown. That's what you're asked to find. Then our K or rate constant given to us as 0.21 per hour. The time for the reaction is 5 minutes. We'll convert that 5 minutes to hours. You know that 60 minutes make an hour. So 5 minutes becomes 5 over 60, giving us 0.08333 hour. So why did we convert the time to hour? Because the rate constant K is expressed in per hour. So the time and the rate constant must have a uniform unit. You can as well leave the time in minutes and convert the K per hour to per minute. But make sure that the two of them have similar units. They should be in concord or in agreement. So we have in the bracket there explained the unit of the time and the rate constant must be uniform. Now we converted. We now bring in equation 14, which is the integrated form of first order equation. 2.303 log AI initial all over AT, concern at time T equal to KT. We modifying equation 14 with the given substance. We now change equation 14. What we now use, we use A as sucrose formula. So we now have 2.30 log C12H2O11. Then I after the bracket, meaning initial concentration, all over C12H2O11T, meaning that is for AT equal to KT. So we now say let, we're going to replace, since we're looking for the concentration of sucrose at time T, we now say let C12H2O11 T equal to AT. So we can don't work with both those values, modify it. So we now substitute the given values into the modified equation. We now have, remember that the initial concentration of sucrose is 0.01. So we now substitute, replace C12, the numerator, C12H2O11I with the value given in the equation, the initial concentration, which is 0.01. And then we're looking for the concentration of sucrose at time T, the denominator what we're looking for. So we'll leave it as AT equal to the rate constant given to us as 0.21 per hour the time in hours is 0.08333 hour. So making correct substitution with the information given to us. And then we now, what we're looking for is inside log. So we cannot easily just solve like that. We have to first of all remove the 2.303 on the left hand side. Divide both sides by 2.303. We now have this expression. 2.303 cancels out 2.303, and then the right hand side we have everything all over 2.303. We solve further. We now have log 0.01 all over 80, having cancelled out 2.303 on the left hand side, equal to, solve the right hand side, 0.21 times 0.08333 all over 2.303. That gives us 0.00760. So having done that, so we want to remove the log. How do we remove the log? We're taking logarithm on both sides. We take log on both sides of this equation. How to take log? You just cancel log on the left hand side, remove the log on the left hand side, and find the anti-log of the right hand side. So taking logarithm on both sides, cancel log on the left hand side, and find the anti-log of the right hand side of the above equation. So when you cancel the log on the left hand side, left with 0.01 over 80. You now find anti-log of 0.00760. So from your 4-figure table or your calculator, the anti-log of 0.00760 is 1.018. So we are left with 0.01 all over 80 equal to 1.018, which is the anti-log of the right hand side. Then cross multiply, so I can make that concession 80 the subject. So comply and make 80 the subject formula. How do cross multiply? We'll give the right hand side a denominator. So what should be under the right hand side should be 1. We have 1.018 all over 1. We now cross multiply. We have 0.01 multiplied by 1 equal to 1.018 multiplied by concession of A at time t. That is 80. So we now have 1.01880 equal to 0.01. Divide both sides by 1.018. Why do we divide both sides by that? Because we want to make the 80 the subject. So we divide both sides by 1.018. 1.018 cancels on the left hand side, and then you have on the right hand side 0.01 all over 1.018, and that will give us 0.00982 mole per dnq. So the remaining concentration at time t, that's 80, which is sent as C12 heading to O11 at time t, is 0.00982 mole per dnq. We'll now go over to half-life of a first order kinetics. The symbol to represent half-life in this tutorial is T-half for half-life. So half-life is another useful tool to measure the rate of a chemical reaction. So it reads, another useful measure of the reaction rate is the reaction half-life, depicted as T-half. Then what is half-life in chemistry? The half-life of a reaction is defined as the time required for the concentration of one of the reactants to decrease to half its initial value. The time required for the concentration of one of the reactants to decrease to half its initial value. So in order to derive half-life equation for a first order kinetics, we recall equation 14. That the integrated first order equation. We bring back the equation 14, which is 2.30, the modified form, 2.30 log AI all over AT. AI, remember, is the initial concentration or concentration of the substance at time 0 before reaction started. And then AT, the concentration of the substance after some time T, equal to KT, that equation 14. So from here we can derive the equation for half-life. What do? Replace T in equation 40, replace T with T half, meaning half-life. And replace AT with AI over 2, because half-life is the time taken for the concentration present to the K to become half of the initial value. So at half-life, AT becomes the initial concentration, that is AI over 2. So we're going to replace T with T half in equation 14 and replace AT with AI over 2 in equation 14. So we'll now go forward. We have 2.30 log AI. AI remains the numerator, all over AI over 2. That AI over 2 is now your AT being AI over 2. Then replacing our K, our T, it should be KT before. Then that T now becomes T half. Then some the left hand side, we have 2.303 log AI over 2 all over AI. Why? How do we get that? Well, remember that they're both expression AI, that is AI divided by AI over 2. And when you're dividing fractions, you have to invert the denominator. So inverting AI over 2, we have 2 over AI. So that's how we got that expression. So log AI times 2 over AI, and AI cancels AI, equal to KT half. So we are now left with 2.30 log 2 equal to KT half. And log 2 is 0.3010. So 2.303 times 0.3010. So give us 0.693 equal to KT half, where T half the half-life. So we make T half the half-life the subject. So how to make the subject? We divide both sides by K, so that half-life becomes the subject of the formula. So dividing both sides by K, the rate constant, to make T half or half-life the subject of the formula, we now have T half as 0.693 over K. So that's what we did here. Divide both sides by K. So you now have 0.693 over K, and then on the right hand side, K cancels K. So how that expression T half as 0.693 over K, equation 15. So equation 15 is the equation for half-life of a first order kinetics. T half equal to 0.693 over K. So it's not difficult to memorize. T half equal to 0.693 over K. That 0.693 is a constant in that formula. You see the derivation which have been done just a few minutes ago. We will now look at that exercise. So it says, consider a reaction with the rate expression R equal to K multiplied by cos of A, that's A, big A in square bracket, and K is equal to 3.33, you know that K is the rate constant, times 10 power minus 6 per hour. Number 1 says, determine the half-life of the reaction. Number 2 says, how long will it take the concentration of A to drop from 1.0 molar to 0.20 molar. So there go the solution. Solution for number 1 part of the equation. We're looking for T half, that's the half-life. And we're given the rate constant, which is 3.3 times power minus 6 per hour. Remember equation 15, the equation for half-life. We apply equation 15 and substituting the value of K. Equation 15 is T half equal to 0.693 over K. The value of K is already given to us as 3.3 power minus 6. We substitute 0.693 divided by 3.3 to power minus 6 per hour. We now get our half-life, which is 2.10 times 10 power 5 hours. So this is the half-life of the reaction. And remember that the reaction is the first order kinetics. How do you know it's first order? Look at the rate equation. Rate equal to Ka. The substance A is rate power 1. So B rate power 1 means it's the first order reaction. We now go to number 2. Number two question we ask how long, that is time. How long will it take the concentration of A to drop from the original value 1.0 m to a new value 0.20 m. So how do we solve equation 2? In equation 2, since it's a first order reaction, we'll bring back equation 14, which is the modified integrated first order kinetics. 2.0, which we used previously. 2.303 log AI initial concentration all over AT equal to KT. So we substitute Our AI is the initial concentration, which is given to us in the equation. So let's go on. Let's follow the same pace. The reaction is first order because the initial rate of the reaction is given as R equal to K times A inside square bracket, and that A is raised power 1, as I explained before. So initial concentration of A, which we can take as AI, is given to you in the equation as 1.0 mole per dm³. Then concentration of A after time, some time t, which is AT, is given to you as 0.20 molar or mole per dm³. The rate constant is 3.33 times power minus 6 per hour. We're looking for time because they say how long, that indicates time. So substitute the given values into equation 14. Equation 14 have been mentioned before, that is the modified equation. We'll substitute this value. AI is the initial value, and then AT. The initial value is 0.1 given the equation. Then the concentration after some time t is 0.02. So let's be sure of it. Okay, the initial value is 1.0 AI, while the concentration after some time t is 0.2. You can see them listed here. So we substitute in that formula. We have 2.303 log 1.0 be the initial, all over 0.2, that is 80, because after some time, equal to our K, which is 3.33 power minus 6 multiplied by T. Then if you divide 1.0 by 0.2, you get 5. So we now have 2.303 log 5 equal to 3.33 power minus 6 T. Log 5 is 0.6990. So we now have 2.303 times 0.6990. That gives us 1.6098 we have under, equal to 3.33 power minus 6t. We want to make t the subject. Divide both sides by 3.33 power minus 6 to make t the subject of the formula. So divide both sides by that. We now have the left hand side 1.6098 divided by 3.33 power minus 6. The right hand side 3.33 power minus 6 divided by the same value. So you look at the right hand side, 3.33 times power minus 6, it cancels out. So we now have t. We divide the left hand side 1.6098 by 3.33 power minus 6. It gives you 4.83 times the power 5 hours. So that's the time we're looking for. Look at nice size that says the decomposition of nitrogen 5 oxide to give nitrogen 4 oxide or nitrogen dioxide, and oxygen is given as follows. Look at the equation that shows the decomposition of nitrogen 5 oxide to give you NO2 and oxygen. Okay, the rate has a rate expression given as rate equal to K bracket opens N2O5 bracket closes. If you look at the rate equation, that reaction is first order because N2O5 is raised power 1. After the bracket, the power on it is 1. Where K is equal to, that the rate constant equal to 5.0 times power minus 4 per second at a particular temperature. One says, what is the half-life for the reaction? Number 2 says, how long does it take for N2O5 concentration to drop to 1/10 of its original concentration? So let's start with the first question. In the first one, we have to find the half-life. We're giving K. K is 5.0 power minus 4 per second. That K is the rate constant. We're looking for T half, the half-life. That connected by equation 15, which you got initially. T half is 0.693 over K. We substitute 0.693 all over K is 5.0 power minus 4. One divide, we have 1386 seconds as our half-life. So, having done that, go to question 2. Question 2 says, how long, that means time, how long will it take the concentration of the reactant, that N2O5, to drop to 1/10 of its original concentration, to drop to 1/10 of its original concentration. So we don't know the original, but let's see how we can do it. Question 2 says, initial concentration of N2O5, which you can take as N2O5 in bracket I. That I means initial. So we don't know the value, we assume that let it be equal to S. Then concentration of N2O5 after T seconds. So the question says how long will it take the initial concentration to drop by 1/10? So after some time now, the concentration of the substance N2O5 will now become 1/10 of the initial, that is 1/10 of S, since we take S as the initial. And 1/10 of S is something as just saying 0.10 S or 0.1 S. Then we're given the rate constant. The rate constant is in the question given to us at 5.0 power minus 4 per second. We're looking for time, how long. So look at equation 14 down there. Equation 14, which is the modified integrated form of first order. 2.303 log AI, meaning the initial concentration, all over AT. Concentration after some time, T equal to KT. We modify this equation. What do we do? Replace the A in the square bracket with the reactant, which is N2O5. So we have under 2.303 log N2O5 in square bracket I all over. That means initial concentration over N2O5. Then T subscript T. That means concentration after some time T equal to KT. Substitute the appropriate values into the above modified equation. So we're going to substitute the value given to us. Remember that we took the initial concentration of that substance N2O5 as S. So we're going to have 2.303 log S all over. Then the concentration after some time T is 0.1 S because it's 1/10 of the initial, as we explained before. That is 0.1 S equal to 5 times power minus 3. That is the rate constant multiplied by T. We're looking for time T. So you see that from that expression, S can cancel S, remaining 1 over 0.1. And 1 over 0.1 will give us 10. That will have under 2.303 log 10 equal to 5 times power minus 3 T. And log 10 is 1. So we now have 2.303 log multiplied by 1 equal to 5 times power minus 3 T. We want to make T the subject. To make T the subject, we divide both sides by 5.0 times power minus 3. So making T the solve the formula by dividing both sides by with 5.0 power minus 3, we have the left hand side becomes 2.303 because 2.303 times 1 will give it 2.303 divided by 5.0 times power minus 3 equal to 5, the right hand side 5.0 power minus 3 T divided by the same 5.0 power minus 3. And similar values, 5.0 power minus 3 cancels out 5.03 power minus 3, remaining T. So our T now becomes, if you divide the right hand side 2.30 by 5.0 times 10 power minus 3, you're going to get 4606 seconds as our time. So that brings this lecture to an end. The integrated form, integration of integrated form of first order equation, or integrating the differential form of the first order equation, and the calculations involved in it. So by the end of this lecture, you see you are done. You'll be able to do calculations on first order reactions and be able to derive the integrated form of first order equation. Likewise, the half-life equation for first order reaction. So next, in this under this chemical kinetics, we're going to look at derivation of integrated form of second order kinetics and calculations. So thank you for staying tuned to the channel. Subscribe to the channel. Move up to the channel's name, Best Science Brain. Under it, you're going to have the subscription bell or icon as the video is playing. Tap on it once and get subscribed for all the videos coming from this channel, coming your way from this channel. Like and make your comments. Ask your questions in the channel. I will also reply it. Share our videos. Share out our videos to students in tertiary institutions, those in second year, those offering these courses as part of their coursework, either in their second year or first year that did the calculations, or those doing postgraduate studies in chemistry related courses or master's degree in physical chemistry. So stay connected and always stay tuned. If you are subscribed, don't subscribe again. So if you are not subscribed, you are seeing the video for the first time, from whatever place you are watching this video, from whatever country you are watching this video, you tap on the subscription button and get subscribed, share videos, and invite your friends as we learn chemistry, physics online. Stay connected. Thank you very much.